Okie dokie, welcome back to your favorite chemistry teacher, Ms. Zun, and your second favorite chemistry teacher, Mr. Saracola's lecture series on Unit 1, Introduction to Chemistry. We love to have you here. Welcome, welcome. Also, for your guys' information, all of these lectures are going to be organized into a YouTube playlist, so if at any point in time you want to go back, you can just go to the YouTube channel for this course. I think it's under my channel name, Erica Sun, ERAKASUN, and you can find any of these lectures. We will also be posting the link to this playlist at the top of our Google Classroom, so just so you guys know, like and subscribe. Oh God. Okay, so moving on with our lives. 1.2, changes in matter. So last time we went over what is matter exactly, what is chemistry, what are we trying to sort of find out by studying chemistry. And chemistry is in essence the study of matter, the study of physical stuff, right? So the essential knowledge that you guys are going to try to internalize for this particular lesson is that different structures of matter means that this matter has different properties. So ice is frozen water, right? It is water in a solid form, whereas liquid water is still water, but it is in its liquid form. And so because they have different structures, they have different properties. So I want you guys to think kind of as a do now at home. Is salt water a pure substance or is it a mixture? And remember, a pure substance from yesterday's lecture is an element, right? Or is it a mixture? And we're going to be going over this answer in class, so just write it down on your handout, and we will go over whether or not you are correct. So, different states of matter. As I mentioned, ice is a solid form of the matter that is water. Remember, water is a form of matter. It's a physical substance, right? So a solid, its particle diagram, the configuration of its atoms in 3D space, kind of looks like this, right? All the atoms are very tightly clustered together and rigidly conformed, right? So, and it makes sense, right? If you touch the top of your table, if you touch the laptop, these are all solids, and they are all rigidly conformed. They do not, for the most part, their atoms don't yield very easily. So the properties of a solid are that solids are rigid, they are fixed in shape, and they are fixed in volume, okay? So what does that mean? It means, for example, if you take your laptop, it's really hard to change its shape, right? You'd have to do something pretty extreme to it to change its shape. And the amount of space that it takes up is always going to be the same, okay? So contrast that with the particle diagram for a liquid. You can see here the atoms are still close together, relatively speaking, but they're a lot more loosey-goosey, right? They slide against one another a lot more easily than in the rigid particle diagram for the solid. So the properties of liquid, if you think about liquid water, which is probably the most salient example, is that they are not rigid. Liquids are not rigid. They have no fixed shape. I like to say liquids conform to the shape of their container. So if you pour water from, let's say, a tall glass into a bowl, right, its shape changes. It conforms to the shape of the container. When the water is in the tall glass, it's tall and narrow cylinder. In the bowl, it's sort of this short and wide half sphere, right? However, the amount of space that it takes up is still the same. So liquids have a fixed volume, right? 1 liter of water is 1 liter of water, no matter how much, what the shape of the container it takes up is. and contrast that with a gas. So here you can see, note closely these three little lines behind each molecule of gas. This is intended to indicate motion, very fast, like this. Imagine this is a gas particle that's moving back and forth and bouncing off the walls of its container. Okay, gases, like think about the air. It contains lots of gases: nitrogen, oxygen, carbon dioxide, right? These are not rigid. It would really hurt if they were, because imagine taking a step and running into a solid wall of gas. That just doesn't happen, right? Gases have no fixed shape, and they also have no fixed volume. Because they are so far apart, the molecules are so far apart, and they tend to bounce around their container. You can make a container really, really large or really, really small, and all of these gas particles are still going to fit within it. So that's what we mean by no fixed volume. Okay? So these are generally, within the scope of Regents chemistry, the three states of matter, the three types of states that matter can take up. So a matter can either form a solid, a liquid, or a gas. And in the form of water, for example, it's solid form. Water is a form of matter. Solid water is ice. Liquid water is what we refer to as water. And gaseous water is what we refer to as water vapor. If you guys have ever boiled water and sort of held your hand over it and you feel something condensing on it, that's the water vapor, right? Okay, so physical properties can change, right? Like a matter's physical form can change. So in a physical change, matter changes form, but not its chemical identity. So yesterday in class, we went over these sort of chemical formulas, right? This is H2O, 2 hydrogens, 1 oxygen. And that is the chemical formula of water in its liquid form, right? And it can be boiled off into to form H2O in its gaseous form. That's what this little italicized G is. But you'll notice that the chemical formula, H2O, stays the same, right? So its chemical identity is the same, even though its physical state has changed from liquid to gas or from gas to liquid. That's what these two little arrows mean, okay? So examples of physical properties that can change without its chemical identity changing is an object's shape. So kind of like this piece of paper, even if you cut it up or cut it into a different shape, it's still chemically paper, right? Its color can change without changing its chemical identity. Its size can change if you cut this piece of paper up into a bunch of little pieces. It's still chemically paper. Its phase can change, okay? So like liquid water to gaseous water or gaseous water to liquid water, that phase of matter can change. And its melting or boiling point can change without changing its chemical identity, okay? So these are really important to remember because you guys are going to be put to the test over how well you understand this in just a little sec. So physical changes. If you look as a solid, what does a solid do when it changes to a liquid? If you look at this ice cream cone, right? Anyone who's ever eaten ice cream in 100-degree weather will know that solid turns to liquid real fast. And that we refer to as melting, okay? It's melting point or fusion. So everyone knows that the melting point of solid water into liquid water is 0 degrees Celsius or 32 degrees Fahrenheit, right? So that is its melting or fusion point. That is also liquids. We'll go over that in just a sec. I'm getting ahead of myself here, okay? And then what about liquid to gas? So liquid water can change to gas at its boiling point or evaporation point or point of vaporization, okay? And so we know for water that is a 100 degrees Celsius benchmark, and I think, don't quote me on this, 312 degrees Fahrenheit? I really don't know. I don't deal too much in Fahrenheit as a chemistry teacher. Okay, so it's boiling point. So sometimes solids can go straight into gas. Anyone who has ever worked with liquid nitrogen knows you can go, or dry ice as it's more commonly known, if you've ever received a package that's just dry ice. The solid ice is sublimating directly into a gaseous state, so it skips that liquid phase of matter. That is possible. It's not magic, it's chemistry. Okay, so this is where I was getting ahead of myself a little bit. All right, the same temperature that solid melts into liquid, liquid freezes into solid, right? So at 0 degrees Celsius, liquid water can freeze into solid ice. Poor Squidward, right? This is also referred to as its point of solidification. And similarly, okay, at the same temperature that liquid water boils into gaseous water, okay, gaseous water can condense into liquid water. And I'm just using water here as an example. This is any physical substance, okay, any physical matter thing. Wow, I'm so eloquent, guys. Okay, so it can condense at the same temperature as it vaporizes, all right? So chemical properties can also change. So you'll notice over here we have 4 hydrogens, 2 times 2 is 4, okay, plus 2 oxygens. All right, so these are what we refer to as the reactants of the chemical equation. I will move my cursor so this little thing moves. And then we also here see that it forms the product. 4 hydrogens over here and 2 oxygens form 2 water molecules, okay? So you'll notice over here the chemical formulas of the reactants are different from the chemical formula of the product. Does everybody see that? Okay, so that is when you know through a chemical equation that a chemical property has changed. So in a chemical change, an entirely new product, different type of matter is formed. And this is where chemical firms like Dow Chemical make the big bucks, right? They make new types of plastics from different reactants over here, different types of plastics. Most of our clothing is made out of plastic, which is kind of scary. Like nylon is a form of plastic, Teflon, Kevlar, all of these are plastics. And so the identity of the substance changes. So you can make a ton of money in chemical industry this way by forming different useful products via chemical changes. Okay, so the signs of a chemical change are that a new substance is formed with different chemical properties. Fizzing is a good sign of chemical change, or an unusual color change. Remember, sometimes color changes can be signs of physical changes, not chemical ones. But if there's an unusual color change, that is usually the sign of a true chemical change. Okay? So oftentimes, you will hear of a chemical change being described as like water combines with blank, or water reacts with blank. So in this case, it would be hydrogen gas reacts with oxygen gas to form liquid water. Or it would be hydrogen gas combines with oxygen gas to form liquid water. So that type of vocabulary within the Regents examination is almost always indicative of a chemical change. Okay, so here are some examples of physical changes that we're going to go over really quick. So remember, in a physical change, matter changes form, but not its chemical identity. So melting ice and conversely freezing water is an example of a physical change because it's still H2O, right? Chopping wood, both halves are still wood. Mixing gray and green marbles, they are still marbles. Okay, and shredding paper, if you ever have some sensitive documents that you would like to keep private or hidden from Uncle Sam, You shred your documents, but that paper, whether or not shredded or unshredded, is still paper. Okay? In a chemical change, a chemical reaction occurs and new products are formed. So, for example, burning wood. Anyone who has ever camped or burnt wood or paper knows that what's the end product of burning wood? Once this wood has burnt, what does it turn into? Charcoal or ash, right? So charcoal and ash are not wood. They have completely different chemical properties from wood because the fire, this heat of combustion, has changed it at a chemical level. Rotting fruit, anyone who has ever tasted rotten fruit will know that that banana is no longer really banana, right? The chemical change, this form of decomposition and decay, has caused a chemical change within this used to be a banana. Okay, fireworks are an example of a chemical reaction where this gunpowder transforms into light and heat, which is really kind of cool. Mixing vinegar and baking soda, you can freak your mom out and can get a good spanking by doing this all over your kitchen. You'll notice lots of fizzing. Remember, fizzing is one of the signs of chemical change happening right here. So, we are going to, in class, complete an activity where you are going to go through a set of scenarios, observe the set of scenarios, and determine whether or not the change is physical or chemical. And some of these are going to be really tricky, so make sure to review your notes prior to coming into class or dialing into our Google Meet, and you are going to support your answer using evidence from the demonstration as well as from your notes. Okay? So, see you tomorrow, guys.